Hello, welcome to the lesson on application of vectors. So in this unit, or in this particular lesson, I'm going to take your knowledge of geometric and algebraic vectors, which you've been working on in the previous lessons. I want you to solve real-world applications. So this is going to be the trickier one because you're going to have to decide, am I going to use algebra or am I going to use geometric processes? And the final answer is really, doesn't really matter. Either one will get you the correct answer. One's more efficient than the other. Some of you are going to say, I just want to use algebra all the way through. Well, there's a time and place for everything, and I'll show you why. Okay, so for this section, you do need to know Newton's three laws, and I have no in quotations because you're not going to be tested on it, and it's really only the second law you really need to know, and I'll explain the why, and I'll try to avoid it in the assessment because I know not everyone has taken the physics. So Newton's three laws, keep it simple: an object in motion will stay in its current state of motion until acted upon by an unbalanced force. All right. So that one, again, it's really the second one. The second one is F equals ma. Okay, and that's Newton's famous second law. And that calculates force. Mass of the object, m. So we have F is force, m is mass, and a is acceleration. Okay, and if we're talking about Earth's gravity, we are going to set a equal to 10 meters per second squared. It just makes the math easier, and it's a vector, so acceleration is always downward. Newton's third law: every action has an equal and opposite reaction. There we go. So again, if you haven't taken the physics, don't panic, please. Okay, it's really all we need to do. You need this formula, okay? So I just want to do all three laws so you can say you learned some physics today too. Okay? So let's look at some examples here. Hanging sign, okay? A 5 kilogram sign. So the mass of this sign is 5 kilograms, and it's suspended. We want to find the tension. Okay, tension is vectors. So we want to find the tension in each cable. So we want to find, and it doesn't matter how you label them, tension is usually your T's, T1 and T2. So you can do this with algebra. Does not matter. Tension is always drawn away from the point of hanging. So if I want to convert that to a vector diagram, tension 1's pointing in that way, tension 2 is in that direction. So there's your T1 and T2. Now there's the force due to gravity here, and that's why I had to teach or just review physics. So F of G is ma. It's a 5 kilogram sign. Gravity is 10, we're saying. So it's 50 newtons. So there we go. That is your three forces. So you need to add our three forces together. Now, because the object is stationary, all right, so I'm going to add a couple of notes in here. Because the object is not moving, and hopefully most signs are like that. Falling signs are not a good thing. Because the object is not moving, the resultant will equal 0. So I'm just going to use short form for resultant there. So our magnitude of our resultant will be 0. Okay? So that means that those three vectors, when we add them up, they will equal 0. So in terms of algebra, we know it's going to equal 0, so it works out fine. I'm going to do this one doing geometric just to show you sometimes it is quicker to do geometrically. So if I was to draw those three vectors, because they add up to 0, that means that the three vectors have to end up forming a closed triangle, because the resultant has to be at the tail, or the head and the tail have to be in the same location when you add the vectors together. So if I add, or I draw in T1 in that direction, T2 is going to be in this direction, and then the force of gravity will close the triangle off for us. All right. Now I know the force due to gravity is 50 newtons, so I know that value. It's my angles now that I have to check or test for. I know that T1 makes a 60 degree with the horizontal, so if I was to draw in some horizontal lines here, so I'm just dashing them in with green, I knew that this angle was 60 degrees here. From the Z pattern, back to grade 9, I know that this is 60 degrees. The force due to gravity is always pointing straight down, so that angle has to be 90 degrees. So that internal angle is 30 degrees. Now what about the other one? T2 makes a 45 with the horizontal. Well, if that's a 90 degree angle, that has to be 45 degrees. So now, when I want to find that third angle in the triangle, 45 and 30 is 75. So that angle is going to be 105 degrees. I now know one side and I know all three angles. So technically, I can use my sine law here. Okay? So using the sine law, I know that force due to gravity over, we'll call it sine A, is equal to the magnitude of the first tension over sine B is equal to the magnitude of tension over sine C. So there is your sine law with vector notation. So I know force due to gravity is 50 over sine 105. I'm looking for tension 1, so it's an unknown, and its angle would be the sine 45. And finally, tension 2 would be sine 30. Sine law breaks apart. And what's nice is we can solve immediately for each of these tensions. So if you do have a hanging sine question or an object hanging question, I do recommend sine law, just because it is a lot more efficient than the algebra. It actually is quicker, but it is a little bit trickier because you do have to draw the picture properly. So I'm just going to leave it in that form. You can actually go ahead and calculate it. But that is the answer right there. And the other one, sine 105 equals T2 over sine 30. So tension 2 is equal to 50 sine 30, also over sine 105. And that would be in newtons. So there's your two answers. There is the tension in the first cable, and there's the tension in the second cable. If you would have done it algebraically, it would have also worked out just fine. So you can go ahead and use all algebra. It doesn't matter. You'll still get correct answers. So in the second example, I'll use algebra. So it says Chris and Josh are pulling a sled as shown. So this is a top view. Josh is pulling with 70 newtons. So I'm going to use this as my J vector for Josh. And Chris is pulling over here with the C vector. How hard does Chris have to pull so the sled is traveling straight? So we're looking for the force. We know Josh is pulling with 70. Got to find out what Chris is going to pull with. So if we go through, and I'll do this one algebraically, just to keep it balanced, to see both. The Josh vector plus the Chris vector. It's going to give me the resultant vector. Now what do you know about the resultant vector? If we want to keep pulling this straight forward along the dashed line, okay, if I want to stay on this red line that I'm drawing in, that means the sled has to go perfectly left and right, which means that there can be no J component in my resultant, okay? Because I can't be pulling it up or down. So the resultant, when you add everything together, it has to add up to 0, okay? So using a vector, algebraic equation of a vector, we know that the Josh vector will be 70 cos 30. I better get it right when I do the video here. Cos 30 I. So that is pulling it. It's going to the right and up, so it would be positive. So plus 70 sine 30j. The Chris vector. It's going to the right, but I don't know the magnitude, so it is going to be an x. That should be a 70 up there. People are saying that I didn't put the 70 in. You're right. 70 cos 30. X cos 50. I Now, I shouldn't put the plus in. Now he's pulling downward here, so it'll be a negative. So minus x sine 50j. All right. We're looking for the value of x. So if you look at it, I don't know what the value is going to be in here. Okay, you can go ahead and add this column. You're not going to be wrong. But we don't know what it's equal to. If we look at the other one, though, I'll do it in green, we know the first number, 70 sine 30 is just a number. Now it's equal to 0. If we take the y component, so I'll say using the y component, we can solve for x here, because 70 sine 30 plus x sine 50 has to equal 0. You just got one variable there. Okay? So if we go ahead and sort it out here, oops, and you know what? I didn't mess up. You don't have to erase anything. Don't panic. Okay, that should have been subtraction. So if you just scratch out the sign in between, minus. So solving 70 sine 30 equals, I'll move x sine 50 to the other side, divide both sides by sine 50. We have our answer. So the algebra here was pretty slick. Worked out all right for us. So x is equal to 70 sine 30 over sine 50 newtons. And you can calculate that out. I'm just leaving it as is. So therefore, crest pulled with whatever that calculates to. I don't want to grab a calculator, so I'm just going to leave it in the exact form. But you can use it as, you can calculate it as decimals. Okay, so there you go. There's the second example with the algebra. So you can see that there's a time and place. If you have hanging objects, much more efficient to use the adding and subtracting geometric vectors. So draw the picture, use sine law. Cosine law we don't need, and the reason you don't use cosine law here in that final step is the resultant 0, so the direction doesn't matter. So we don't have to use that cos to find that angle. Similarly here with the algebra, you don't have to solve for everything. You're basically trying to figure out what's unknown. So a couple more examples to run through, and then you're allowed to go ahead and try some of these applications.